welcome. Today we'll be tackling the final question in this chapter, question 14, which is as follows. To each mapping f from A to B, associate the mapping f star from the power set of A to the power set of B that associates to any subset, x is a subset of A. The image under this mapping, f of x, is a subset of B. Then we'll note that the mapping from f to f star is another mapping phi, which associates to any mapping f in the set B to the A, another mapping f star in the power set of B to the power set of A. The question is this mapping phi injective, surjective, and why? Take a couple seconds to consider the wording of this problem, what it's really asking. Then I'll give you some hints. Then we'll go on with the solution. All right, let's start with the hints. And the first hint is just going to be clarifying the wording of this problem. So we'll look at the mapping phi, and we'll note that the set of B to the A, we're going to write that here, is the set of all mappings from A to B. So, in particular, if we draw this as an abstract blob, it's the mapping F1 all the way, arbitrary mappings Fi from A to B. Next, we'll look at this set on the right, the power set of B to the power set of A. And this has a bunch of other mappings. We'll call them F star 1, call maybe F prime 1, all arbitrarily many of these. But we'll note that these mappings take subsets. So for instance, the set of A to the set including just the element B. Perhaps this is our definition for F prime 1. Meanwhile, this might be associated with the map F1, which simply sends the element A to the element B. The difference being F1 prime acts on subsets and it outputs subsets. Meanwhile, F1 takes elements and sends them to elements. With that, some other hints might be, if we want to show that something's injective, recall that injective means either that if the outputs are the same, then the inputs must be the same, or equivalently, that if the inputs are different, then the outputs must be different. For surjective, to show something surjective, we must show that every element in this set, namely every mapping of this kind, can be mapped to under phi. All right, let's begin with the solution. I'll start in the reverse order. Let's show that phi is not surjective. So we're going to show that there exists a particular element, a fn prime, such that there is no map fn where phi of fn is equal to fn prime. And we can do this just by counterexample, where we will let fn prime be special in the sense that if we have the cardinality of B is bigger than the cardinality of A, namely that has more elements, there exists a particular map, which we'll call maybe f prime t, the total map, which associates the element, the set of A, and sends it to the element of the set of B. And this is a well-defined map in the power set of B to the power set of A, in that these are two well-defined subsets in their respective domains. The set of A is a subset of the power set of A, and the set of B is a well-defined element of the power set of B. However, we will note that there is no map that has this being the case. This is because, as we mentioned, the cardinality of B is greater than the cardinality of A. So this would be a map that sent one element in A to multiple elements in B, which is impossible because mappings, by definition, send one element to exactly one other element. So, or at most one other element in B. So, since there's no mapping that has this, then our map phi will never send any, there's never any map to fill in here such that phi of that is equal to f, the total map prime. This is not possible. So therefore, since there's an element in the codomain, the power set of B, in the codomain, the power set of B to the power set of A, namely this special map, the total map, there is, since there's nothing that gets sent there, it is not a surjective map. Meanwhile, let's consider injectivity in this little space we have in the middle on the left. For injectivity, let's use that we have equal outputs, and we're going to show that implies equal outputs. So let's consider phi of f1 is equal to phi of f2. Well, that means we can associate these with maps f1 prime and f2 prime, which are going to be equal. But this means for these two to be equal, that means for any subset X, the image set f of X is, that means that each of these maps f1 prime and f2 prime send any set X to this image set, the set of f of X, for all sets X. That means no matter your input, they always get sent here. But that means that f1 is the case that any element, any set X, will always be sent. Then we have that f1 of X is equal to f2 of X for all X, since the output sets have to be equal. But since f1 of X is equal to f2 of X for every possible set X, then clearly f1 is equal to f2, since any two mappings are the same if they send the same sets to the same sets. Therefore, we have equal outputs implying equal inputs, so the mapping phi is injective. One thing you might note is that you might superficially say that the mapping phi is not injective if you consider the case of perhaps sine of x and sine of x plus 2 pi. These, we'll note, are the same function. Even though they're written slightly differently, they're exactly the same function because they send the exact same inputs x to the exact same outputs. So this is not a counterexample to proving injectivity. So you can have different representations, but at its heart, these two are the same function. So we have equal outputs implying equal inputs. So the mapping phi is injective, in fact. We've now shown that phi is an injective mapping, but unfortunately not surjective. So additionally, we can note that phi is not bijective, but where it's well defined, it does create a natural bijection between the image, the domain of phi and its image space. And with that fun little fact, we are done with chapter 1, and I hope to see you in future videos. Thank you.